So last time we've discussed up to the beginning of sound, where we understood the general equation of sound waves. So we saw that sound can be described as either displacement, longitudinal displacement, or as pressure. It's this kind of an equation that we get, where the relationship between the pressure amplitude and displacement amplitude is given by this. The other symbols have usual meaning. K is equal to 2 pi by lambda. Omega is equal to 2 pi f or 2 pi upon time period. And propagation speed B is equal to omega by K or f lambda. And we have that same relationship that the wave speed B depends on medium. Frequency is the source. Source is property. And therefore lambda is affected by B. So these were the common sort of properties that we saw. Now also we saw intensity of sound. Given by half density into P into omega square into displacement amplitude. This was an important relation. Where we saw first wave speed is square root gamma T by M or square root of bulk modulus by density in fluid medium. Solid medium, of course, bulk modulus is replaced with Young's modulus. So these were all the common features. And now, today we'll start by understanding for audible sound. There are two important ranges. One is the frequency range. That is 20 to 20,000 hertz. So above this it is called ultrasonic, below this it is called infrasonic. So for human beings on an average, the audible sound range has to be in this frequency range. But there is also the intensity range. You can think of intensity approximately as loudness. So that is from 1 picowatt per meter square to 1 watt per meter square. That is 1 into 10 raised power minus 12 watt per meter square. 1 watt per meter square. So why we call this the range is because this level, it is called the threshold of hearing. Typically denoted by I0. So the intensity is less than I0. The sound is inaudible. That is, it's too soft to hear. But this one, it is called the upper limit or the threshold of pain is also an important limit to understand. Typically denoted by I max. So if intensity becomes greater than I max, it is not that it is not audible. It will be audible, but it will also be damaging. Yes. Damaging to hearing. So it can cause permanent damage if you are subjected for too long to that kind of sound, more than threshold of pain. Now, because this range of intensity is very large, it's from 1 picowatt per meter square to 1 watt per meter square. Because of that, and also because of subjectively our perception of sound is on a logarithmic scale and not on a decimal scale. So we define the decibel scale. For intensity. So in the decibel scale, we define intensity of any sound in decibels by this equation, that it is 10 times log to the base 10 of the intensity of that sound in watt per meter square divided by the threshold of hearing. So this is the standard accepted formula for the intensity in decibels. Where of course I naught is 1 picowatt per meter square. That is the threshold of range. So for example, if the intensity in watts per meter square, let us say 3 into 10 raised power minus 8. We want to convert this to decibels. We use that formula. That intensity in decibel will become 10 times log. This intensity in watt per meter square, that is 3 into 10 raised power minus 8, divided by this intensity, 1 picowatt per meter square. This becomes 10 log 3 into 10 raised power 4, as you can see. So that becomes log 3 plus 4 times log 10. So log 3 we can take approximately as 0.48. And log 10 is of course 1. So 44.8 decibels. This becomes the value of intensity in decibels. So this type of calculation you should know. So let's see another question based on decibels. Okay, so try this out. So if the intensity I1 in decibels is 30 decibels and the intensity I2 is double of I1 but watt per meter square, that is in the standard decimal scale watt per meter square, it is twice, double. So how much will I2 become in decibels? Just tell me the answer in decibels, how much it should be. Anyone got the answer so far? See, in this you don't have to do that much calculation. Okay, one is that okay, you can sit and calculate how much I1 is and then calculate how much I2 is. But actually all that is not required. You can use a direct relationship using the property of log. Anyway, if I1 is equal to 30 decibels and I2 is twice of I1 in watt per meter square, you can just use this relationship that 30 decibels is equal to 10 log I1 divided by I0 in watt per meter square. And let's say X decibels is 10 log I2 divided by I0 in watt per meter square. Let us say I2 is X decibels. X we want to find out. Now just subtract these two things. Equation 2 minus equation 1. So x minus 30 becomes 10 times log I2 by I0 minus log I1 by I0. Now use that property of log. So this becomes this divided by this, which further becomes this, which becomes, because I2 was double of that. Now you take log 2 approximately as 0.3. This becomes, or 3 decimal. So this side is x minus 30. X becomes 30. That means I2 in decibels is 33 decibels. Actually, it's very simple. I've written out all the steps clearly, so it looks like it's lengthy, but it's very simple calculation. Yeah, Manishka, your answer is correct. All right, so this is self-explanatory, quite clear. That's how these things work. Okay, now let's move on to superposition of sound waves. So as you know, if the superposing sound is of same frequency, then it is interference. If sources are identical frequencies, the effect is called interference. You have that same formula that if it's on second source, phase difference is delta by. Then your resultant pressure variation is P1 plus P2. That becomes some net amplitude into sine omega t minus kx plus some net phase constant, where once again that net amplitude, the best way to understand it is by phasor diagram. So these are the individual amplitudes. And they are drawn as phasors with these different delta phi. And this becomes the net amplitude. The only thing is here, because we're dealing with sound, so directionality is not important. So the sources could be anywhere. The sound waves could be coming from any direction. So that means any sort of problem is possible now. So for example, you can have 2 point sources of sound like this, S1 and S2. They are creating sound of identical frequency. And there is an observer who is, let's say, over here. This is the position of a detector. Now, given suppose S1 and S2 produce sound of identical frequency 1 kilohertz, and speed of sound is given approximately in air to be 300 meters. You know that at normal room temperature and atmospheric condition, it is close to about 340, 340, but here let's say it's assumed to be this one. Okay. Now also given to us this all parameters, that this distance over here and this distance over here, these two are given. X, Y. So suppose the Y is given as 60 centimeters and X is given as 80 centimeters. And so if sources S1 and S2 are synchronous, and coherent. Coherent means identical frequency. Find phase difference of sound from S1 and S2 at the position of the detector. And secondly, if S1 and S2 are delivering identical power of, let us say, 50 watts each, then find the resultant intensity I net due to interference at the location of the detector. So I'll give you a hint for the second part as well. But first, start with the phase difference. Okay, so calculate this phase difference from the given diagram and the information which I've given you. So just try this out. Okay, so anybody got the phase difference for the first part? So what we have to do is use the frequency and velocity given to find the wavelength, okay? And then find the path from S1 to the detector and from S2 to the detector. So from that we get the path difference. And then just like we had seen in transverse wave last time, so how to convert path difference into phase difference? So that is 2 pi by lambda into delta x. So everybody got it? So everything lies in the diagram actually. In this diagram you can see that this distance, let's say the distance traveled by the sound coming from source S1. So let's write that as x1. So that is square root of x squared plus y squared. X and y was 60 and 80 centimeters. So that's 100 centimeters. And this distance here, which is the sound traveled by x2, I mean from the source x2. So that is equal to x, or that is 80 centimeters. So coming back here, if the sound coming from source S1 is some P1, which is some kind of amplitude, sine omega t minus kx1. The sound coming from the source S2, some kind of amplitude into sine omega t minus kx. There is no other phase factor because the two sources are synchronous. S1 is some amplitude, let's say P0 into sine omega t. Then S2 is also creating sound of impact. So here you can see that phase difference is much. What is the magnitude of that? So 2 pi by lambda into x1 minus x2, because x1 was larger. Correct. Now lambda is equal to p upon frequency. The speed was 300 meters per second. The frequency was 1000 hertz. So lambda is equal to 0.3 or 30 centimeters. And we saw that x1 minus x2 was 20 centimeters. So 4 pi by 3. That is my field difference. That's it. So my cos delta phi term becomes significant. Actually, that is minus cos phi by minus 60. That is minus. This thing here is important. Okay, now next we'll talk about the net intensity. Here, how we relate density. Next thing is intensity due to a point source at a distance x from it. If you have a point source, it is emanating sound of power V watts. And as you know, at a distance x from it, the intensity that becomes that power divided by 4 pi x. This is assuming that the sound propagates equally in all directions. Typically, there are reflections and all from floor, from other obstacles and all. So it doesn't work 100% in real life. But here, we assume that we have an isolated point source and no other obstacles. So, at a distance x from the source, the power gets divided by 4 pi x square for intensity. Because basically, at a distance x, if you draw a spherical surface of radius x, every point on the surface receives equal amount of intensity. The intensity becomes the total power emanated by the source divided by the total surface area, which is 4 pi. So that is how we get this formula. That's one thing we do. Okay. So now if you go back to the question, what I had given in the question is that they are delivering identical power of 50 watts. Okay, so find the resultant intensity. So what will happen is for this problem, S1 is also giving 50 watts power. S2 is also providing 50 watts power. But the position of the detector, it is at different distance from each other. So the individual intensity coming from S1 and S2. This is at a distance x1, 100 centimeters. This is at a distance x2 of 80 centimeters. So intensity of sound from S1, then let's say I1, that becomes that power divided by 4 pi x1 square. And S2 where P is the common value of power for x1 is 1 meter or 60 pieces. So these are the individual intensities. Now we will use the relationship between intensity and amplitude to find out the net intensity. So first of all, understand this properly. Then we will convert the net amplitude formula in interference into a relationship between intensities. So now, how to get net intensity from I1 and I2? Coming back, if S1 and S2 produce pressure amplitudes of P01 and P02 at the position of the detector, then the intensity produced by the first source is directly proportional to P01 square, and the intensity produced by the second one is directly proportional to P02 square, and the net intensity due to interference is directly proportional to the net pressure amplitude. So these three relations will now we know that the net pressure amplitude is such that it is equal to square root of P01 square plus P02 square minus 2 times P01 P02 cos of delta. So squaring both sides, see that net amplitude squared is first source is amplitude square plus second source is amplitude square plus twice of products into cos. Now in this relation, we can use the fact that intensity is proportional to square of pressure amplitude. So the net intensity comes out as this one. Intensity due to the first source plus intensity due to the second source into 2 times square root of product of intensities multiplied by. So this is an important formula, as I'm sure all of you know. It is used a lot in wave optics and in sound. So this is an extremely useful and important formula. So here, our net amplitude will in fact become that common power divided by 4 by x1 square plus 2 times from that same power divided by 4 pi x1 x2. You take the square root term into cos delta, and delta phi was 4 pi by 3. Cos delta phi was minus half. This will in fact become take all these terms common. 1 by x1 square plus 1 by x2 square minus हो जाएगा ये 2.5 that we can see. So 1 by x1 x2. So to get the proper answer now, in this we substitute this as 50 watts divided by 4 pi into 1 by 1 square plus 1 by 0.8 square minus 1 upon 1 into 0.8. So this thing that we get now, the denominator is in meters square. So this will give us the proper value of power, sorry, intensity in watt per meter square. Okay, so this is a more detailed method of, more detailed type of calculation that we do in this problem for the net intensity. Making use of both these formulae. That one is intensity at a distance of x from a source. This one. This formula here. We're making use of that. So we are finding the individual intensities from each of the sources. You know that. And the other formula we are making use of is this one. Once you know this formula directly, you don't need to derive it every time. You can use this formula directly. The net intensity is I1 plus I2 plus 2 root I1 I2 cos delta. Okay, so we'll discuss a little bit more about these formulae, but first note this down. Alright, people, so hope this is clear. So let's look at another type of interference problem. So in these problems now, actually the main issue becomes geometry. How you will use geometry to find paths difference and all these things. Okay. So but before that, before I forget, this formula that we have, this one and the corresponding formula, that net intensity is I1 plus I2 plus 2 times square root I1 I2 cos delta phi. So from this we can see that the maximum becomes P01 plus P02 for delta phi to become 2 and 5. And the corresponding maximum intensity that we get. Here, if you substitute cos delta phi as plus 1, you can see that becomes square root of I1 plus square root of I2. This equation is constructive interference. You should also know this formula I explained. That in constructive interference, the net intensity, which is the maximum possible intensity, becomes root of I1 plus root of I2. Whereas on the other hand, the minimum value of the pressure amplitude becomes P01 minus P02 mod. And this happens for delta phi equal to odd multiple of phi. But this now corresponds to intensity formula of I minimum, which is root I1 minus root I2. This is the condition for destructive interference. And another thing we should know that if P01 is equal to P02 equal to P1, or I1 is equal to I2 equal to I0, then this formula reduces to this, becomes 2P0 cos of delta phi by 2. Formula we can this. This formula four I0 cos by delta phi. So this extra formula basically you can just see it comes from that condition that 2 plus 2 cos delta phi as cos square delta. This is the identity, the trigonometrical identity that we use. So these two special formulae for the situation where the sources are individually producing the same intensity for or the same pressure amplitude at a given point. This is very useful. These are some additional formulae which are very handy. In this one, then the condition for destructive and constructive, and then this one. And also in this specific case, what happens is that I max becomes 4 I naught and I minimum is, or the maximum amplitude you can get is twice P naught, and the minimum amplitude by destructive interference is C. So these are some additional points you can go by. Okay, so let's look at another pattern of problem that we get. Okay. So this example now, what we have is first of all two sources of sound, 2 point sources S1 and S2, which are symmetrically placed with respect to the center of a circle like this. Circle is of radius r, and now a detector who is moving along this circular path. This kind of problem. Now, what is given to us in the problem? That S1 and S2 two sources of sound of identical frequencies. So F is equal to 3 kilohertz. An identical power. $20 watts. Speed of sound. Suppose given to us as 330 meters per second. Right now, if S1 and S2 are placed symmetrically with respect to O in the center circle, radius R, such that S1 S2 is equal to B and S1O is equal to S2O equal to D by D, and R is very large compared to B. Now given that D is equal to 33 centimeters, find the number of positions on the circle at which the detector would experience constructive interference and destructive interference. That's the first thing. And second, find the angular positions for constructive interference. So when the detector is at some arbitrary position like this, let's say, if this is the angle we are considering for angular position, you have to find the values of theta at which the detector experiences constructive interference. That's the last part of it. So just try this out. Okay, so anybody's come up with answer of number of positions of constructive interference? Yes, there's some answer. Just verify. No, not yet. Okay. So see, how much is the wavelength of the sound coming over here? The wavelength of the sound is V by F should be coming as 330 meters per second divided by the frequency, which is 3000 hertz. So that should be coming as 33 by 100, or I mean 11 by 100, or 11 centimeters. So the wavelength should be coming as 11 centimeters. So then you can also see that the distance S1, S2, that distance is 3 lambda. So this should give you a hint of how many positions. Obviously, you assume that, actually, even if you don't assume that the sources are in synchronous, the first part you'll still get. Now, based on this, you tell me the answer of the first part, please. Nobody got, yeah. Manishka, constructive interference will happen in number of places actually, not just three. In one quadrant, it will be three places. Okay, but for the entire circle, you see that if we assume the sources are synchronous, for example, then you can see that, let's say we label this point here as E. So यहाँ पे your path difference is maximum. It's 3 lambda. Whereas suppose this point we label as B. So here your delta x is 0. Then again over here your delta x is 3 lambda. Then again below at that point. At this point, delta x is 0. So delta x is 3 lambda means phase difference is 6 pi. So you're getting constructive. You're getting maximum intensity here. Same over here. Because delta phi is 0. So you're getting maximum intensity here. Same here and same here. Okay. But also you will see that as you go from here to here, there will be some other point in between where your, let's say this point is P1. So this is here your delta x would have changed from 3 lambda to 2 lambda. So here also you will get maximum. And some other point, let's say P2 over here, where delta x would have changed to lambda because it's continuously decreasing. Delta x is this thing. It is this x1, x2. So delta x is x1 minus x2 using that. So your x1 minus x2 is continuously decreasing. So it's going from 3 lambda to 2 lambda to lambda to 0. So three positions, two other positions in between where you will get the maximum. Okay. Now interestingly, there will also be two positions where you get minimum, because in between 2 lambda and 3 lambda, there should be some kind of position where, let's say you get delta x equal to 5 by 2 lambda. So you get your phase difference. So here you get the minimum intensity because here your phase difference becomes 5 pi. And similarly, you get another position here somewhere where your delta x is 3 by 2 lambda. So then you are getting a minimum. And another position here where delta x is equal to lambda by 2. So you are again getting a minimum. So like that, there are three positions here where you are getting minimum, three positions here where you are getting minimum, and three positions here. So total of 12 positions where you are getting minimum, and again total of 12 positions where you are getting maximum. It's symmetrical. Again maximum here, maximum somewhere here, obviously maximum here, then again somewhere here, again somewhere here, then below, then again somewhere here. So getting 12 such positions where you're getting constructive interference and 12 positions where you're getting destructive interference. So 12 positions for delta x to be n lambda and 12 positions for delta x to be n plus half or n minus half lambda, however we write it. Like this. Okay, people, so hope this is clear. Yeah, so that's how you will find. Now the second part is a little bit more tricky in terms of calculation. So let's understand. Okay, now consider so this is where your source S1 is, and this is where your source S2 is. So now if we consider these distances as x1 and x2, okay, from some arbitrary point P, where for that point the angular position is this theta and this radius is r. Okay. So now we want to calculate x1 minus x2 and that. But remember, r is very large compared to b, where this is d by 2 and this is d by 2. Each of these from the center distances are like this. So that is where we'll have to use a bit of trigonometry and this application. Okay, so the center point is O. In triangle S2OP, if you apply cosine rule, x2 is equal to square root of r square plus d by 2 का whole square minus 2 times r into d by 2 into cos theta. This is cosine rule applied. So we can take x2 as square root r square plus d square by 4 minus rd cos theta. Okay. Now we bring in the fact that d is very small compared to r. So d square by 4 becomes negligible here. So this x2 becomes approximately square root of r square minus rd cos theta. And further, you can take r common. So it is 1 minus d by r cos theta to the power half, where again you can bring the power inside, binomial approximation because of this. So d by r cos theta is small compared to 1, so I can use binomial approximation. So this is how I can finally relate my x2 in in terms of theta. Now similarly what we do is you take triangle S1OP, okay, and do all the same steps and find out how much x1 is approximately in the middle. So from that you can relate the path difference x2 minus x1, and from that we can find out at which position we are getting constructive interference and which position we are getting destructive interference. Okay, so hope this method is clear. Now, when you do all this similar type of calculation here for the second part, for x1, you will just get x1 as this. You will find out that x1 comes out to be approximately equal to r into 1 plus d by 2r cos theta. Applying the same steps, okay? Because in that triangle you can see the angle which is the interior angle is pi minus theta. So everything else is the same, but x1 will become this minus cos of pi minus theta. So cos of pi minus theta is minus cos theta. So that's where everything is the same, but this minus sign becomes plus. Okay, you get this. So you get this as x1 and this is x2. So at that general point theta now, okay, so at that point P you can see the path difference. X1 minus x2, that path difference becomes this minus this. So when you work that out, you will see that is equal to b cos theta. Okay. So you will see that for constructive interference, your delta x is 3 lambda, 2 lambda, lambda or 0, whereas d itself is 3 lambda. So your theta is equal to cos inverse 1 cos inverse 2 by 3 cos inverse 3 and cos 0. So this was the point which was at E in our diagram above. This was the point which was B in our diagram above. But these were the other 2 points which I had taken, P1 and P2. And now on the other side, they will be symmetrical. So they will also be in 4 quadrants. So this was in quadrant 1. Okay, similarly, in quadrant 2, you will have all these points. You have pi minus you know, cos inverse 2 by 3, pi minus cos inverse 1 by 3. Those two are the points, and pi, and like that. This is quadrant 2, like that, quadrant 3, quadrant 4. You get all your 4 points. So this is your complete analysis of this. So the points, these were your points P1 and P2. So in between these two extreme points, 3 lambda and 0, you have 2 lambda path difference and lambda path difference. So those are happening at points P1 and P2. So those corresponding points I give. This is your so this type of calculation with approximation and all that is very important for not only this chapter but later in your wave optics also. Okay, so good. You understood all this, Mahesh. You got the value of x1 also correct over there. Okay, people. So let's move on from interference now. Now we'll see that there is also in the case of superposition. Here it is also possible that the situation that we get is superposition of sound from sources of nearly equal frequency, but not exactly equal. So that is, as you know, beats. That gives us phenomena of beats. For example, we have one source which is producing sound at frequency f1 of, let's say, 200 hertz, and another source s2 which is producing sound of frequency 204 hertz. So as you know that a detector anyway will experience alternate loud and soft kind of sound, irrespective of what the path difference and all that is. So he will hear 4 beats per second. He will hear intensity modulation, what we call. That is, the intensity modulates between loud and soft at 4 beats per second. So what will happen here is the sound coming from source S1 and the sound coming from source S2 individually. Suppose they are like this. This is from source S1. Suppose this is varying with time like this. And that one was 200 hertz. So this time period is 5 milliseconds. Now from source S2, the frequency was 200 hertz. So from source S2 also you are getting a very similar kind of sound. There also the time period is nearly the same. Frequency is 204 hertz. So this time period, it says T prime. So T prime is also almost 5 milliseconds. It's a little bit less than 5 milliseconds. But the net intensity that you'll end up hearing is from the superposition of these two. That will be a different story. So what you'll end up hearing here is something like this. Draw this in a different way. You'll end up hearing a sound like this. There's an intensity modulation or pressure versus time. This is where the intensity is maximum, and this is when the intensity will become minimum. Okay. So this is itself going to have a separate time, say delta t. This delta t will be 0.25 seconds because beat frequency we saw was 4 hertz, whereas this time period of the pressure variation, that is the same. That is about 5 milliseconds. So this is visually trying to understand what happens in the case of beats. Now mathematically also it's easy to understand. We'll come back to that. So this kind of situation will create this kind of variation. So as far as your problem solving is concerned, you have to understand just this thing. Now I'll explain to you in a different manner why this happens. Okay, instead of using mathematics, I'll use phasor diagram to understand why this happens. So what is happening is, see, at the position of the detector, the sound from source S1, suppose it is something like this. And from source S2, it is something like this. plus even some phase difference. Okay, where you know that omega 1 is 2 pi f1, so that is 2 pi multiplied by 200 hertz. K1 is V1 by omega 1, sorry, V by omega 1, because sound is after all propagating in the same medium. So it is 1 by 2 pi f1 square root of gamma RT by m. But similarly here in the same equation, what is my omega 2? Omega 2 is 2 pi f2 or 2 pi into 204 hertz in that particular example. Okay. Or you can see it as that 2 pi into f1 plus the beat frequency, because we are taking the beat frequency as 4. So that is my omega 2. And similarly, of course, K2 is V by omega 2. So all these things are the same. Nothing changes. Okay. So these are this. So now you can see that the phase difference at any point of time, that is the difference between this argument, the argument of sign in the first equation minus the argument of sign in the second equation. So at any point of time, so the phase difference delta phi is actually the whole of the second argument. So that is omega 2 t minus k2x2 plus phi minus the first one's argument, that is omega 1 t minus e1x1. Now remember here that k2x2 is a constant. It's not changing with time. k1x1 is a constant, and phi is some kind of phase relation between the two sources. So these three are constants. But this term that you get, omega 2 minus omega 1 into t, this is time varying. It is instantaneous. So we can say that my phase difference, instantaneous phase difference, is this time dependent thing plus some constant. So let's just write that constant as something else. So what happens as a result of this now is my phase difference is time varying. And it is time varying in such a way that this omega 2 minus omega 1 into t, you can see, is 2 pi into beat frequency multiplied by time. So it is that 2 pi into beat frequency multiplied by time plus some constant. This alpha is a constant. It's a combination of all these three things, but it's okay. So now you just think about the phasor diagram. You understand that the net amplitude is going to be that 2 p naught cos of delta phi by 2 kind of term. But here delta phi is time varying. Is that difference? So when you instead of doing the mathematics, now you just visualize the phasor diagram how that works. So you have the amplitude from the first one, the amplitude from the second one, and the resultant amplitude. But you notice here that this phase term delta phi is actually rotating. So this this whole thing is actually rotating like this. It's rotating with an angular speed which is equal to 2 pi f beat, because your delta phi is equal to 2 pi into beat frequency multiplied by time plus some constant. So this whole thing is actually going around a circular path like this. So as it's going around this circular path, you can see that your P net keeps varying between 2 P naught and 0. But this variation happens how many times a second? It happens at the rate. This variation happens at the rate of that omega by 2 pi. Or beat frequency. Or in this case, at the rate of 4 cycles per second. This. So that means your resultant pressure amplitude. We just talk about the pressure amplitude. Okay. That varies with time. At the rate of 4 cycles per second. That means 0.25 seconds. Or even if you think about the net intensity, that varies between 4 I naught and 0 at 4 cycles per second. So you can think of this as like intensity also. So the actual variation of pressure with time become like this. So this is a very easy sort of intuitive visual manner of understanding why beats occurs. Because the frequency being different of the two sources, what is happening is they're constantly going in and out of phase. They're constantly going in and out of phase, these two. So constantly they're creating destructive, constructive, destructive, constructive. Continuously that thing is varying because the phase difference is varying with time. That is where studying this thing. So that's what you have to understand as far as formula is concerned. Okay, people, so hope this is clear. So now the good questions at the advanced level involving beats are always questions where there is Doppler's effect and beats combined in the same situation. So Doppler's effect I'm not going to, so the next phenomenon in sound we'll look at is Doppler's effect. Now that I'm not going to get into the derivation. You can look at the derivation from any standard textbook. But basically you'll understand that, a source of sound, if it is a stationary source of sound, it creates wavefronts which are like this. These wavefronts are increasing in radius at the continuous rate of V, and the lambda between any two of them is equal to V into time period or V upon frequency. But if, for example, we have a situation where you have the source which is stationary, so it's created concentric wavefronts from a stationary point. But we have a detector who's either running in like this at a speed V, or another detector, let's say, who's running away from the source at a speed V, let's say Vd, this is the velocity of the detector, whereas the source is stationary. So this guy will hear a frequency which will be more than the frequency of the source, whereas this guy will hear a frequency which will be less than the frequency of the source, because you can understand from this the wavefronts are traveling at that speed V. So the distance between wavefronts is equal to V into the time period, or V divided by frequency. But for this guy, the distances will appear to be less because of relative velocity. For this guy, the distances will be more. Okay. So as you know, the frequency for this guy will become V plus V of E, or that is the V of the detector divided by V into F. Whereas the frequency for the person who's having a separation velocity of Vd will become V minus Vd upon V times F. Okay. So this is a situation where you have either approach or separation. Now similarly, if you have a situation where your detector is stationary, but it is your source which is traveling towards you, then you can see that right now the wavefront which has been produced is like this. But a little while back, the wavefront that was produced was with some other center, because the source is moving like this. So your wavefronts like this, because this earlier wavefront center would be somewhere here. In the earlier wavefront center would be somewhere here. Then the earlier wavefront center would be somewhere like this. So because the source is continuously traveling like this, so this detector, let's say E, will experience wavefronts which are closer, whereas this detector, let's say B, will experience wavefronts which are more. So the frequency heard by A will be greater than the frequency of the source. The frequency heard by B will become less than. Okay. And here the formula, as you know, becomes frequency by A is V upon V minus the source's velocity, because it's an approach velocity towards the detector. Okay. Whereas the frequency heard by B, for whom there's a separation, becomes V upon V plus Vs. And then you can take a general case where we combine the two things. So we get the general formula that frequency heard by the detector becomes V plus V of the detector upon V minus V of the source, where Vd is the instantaneous component of detector's velocity along this line. Okay, and Vs is the instantaneous component of the source's velocity along this line. Okay. So if you have a general situation where the source is here, the detector is here. Now, if the source is moving with, let's say, some velocity like this and an angle alpha like this, and let's say the detector is moving with some velocity like this, an angle beta like this along from this line. Then over here in this diagram, you can see that your Vs will be the component of this velocity along this line, S to D. So that will become V1 cos alpha, and Vd will be the component of the detector's velocity, that is V2 along this line, V2s. So, okay, so this is the general sort of application of Doppler's effect. So, for example, let's say we have a situation like this now, where something is moving along this path. This is moving at a constant speed, let us say 20 meters per second along this path. And this is basically a source of sound. So it's creating a frequency of, let's say, 200 hertz. Now there is a stationary detector somewhere here. And suppose this distance, let us say 12 meters, and at this position E, this distance is, let us say, 16 meters. Whereas there's another position here, let's say B, and that is 9 meters on this side. So given that speed of sound has an approximate value of 300 meters per second, you have to find the percentage change in frequency heard by the detector as the source moves from A to B. So as the source is moving from this point to this point, what is the percentage change in the frequency that is heard by the detector? Just try this out with them. Assume the source is moving at a constant speed along a straight line. right? So right, so people, anybody got the answer? Right, people. So hope you have got this. So in this case, you can see at this point the velocity's direction is along this line. I mean, the component we'll have to take is along this line, whereas the velocity vector itself is over here. So this velocity vector is 20 meters per second. And you can see that this angle here is going to be tan inverse of 12 by 16 or 37 degrees. Whereas when he's here, let's see, we are denoting the velocity vector like this. So that velocity vector is again 20 meters per second. But the line along which we'll have to consider this now will have to be this line. So we will be concerned with this angle as the same as this angle, which is 53 degrees. Okay. So from that you can see that at E, we will take the component of the source velocity towards the detector as positive of 20 cos 37. So 4/5 of 20, so that is 16. And at B, we will take the component of the source's velocity towards the detector as a negative quantity because this component is actually going away. So it is minus of 20 cos 53. So that is minus of 20 into 4 by 5, into 3 by 5. So that is minus of 12. So the frequency heard when he is at E is V upon V minus 16 times F. And the frequency heard at B is V upon V plus 12 times F. So the percentage change is equal to FB minus FA, that is the change, divided by this, converted into a percentage. So now you can see this is where we can use the binomial approximation method because V is 300 meters per second. So V is very large compared to 16 or 12, comparatively large. So we can use this V upon V minus 16 and approximately write as 1 minus 16 by V to the power minus 1. Actually, this is exact. Next step, we'll do the approximation. This is 1 plus 16 by V. So we can write FA approximately as 1 plus 16 by 300 times F. And similarly, V upon V plus 12 becomes 1 plus 12 by V to the power minus 1. You can approximately write as 1 minus 12 by V. So the frequency at B times F. So the percentage change becomes minus of 12 by 300 minus of 16 by 300 divided by 1 plus 16 by 300. So you can see it becomes minus 28 divided by 316. Convert this into a percentage by doing this. So this becomes the easy way of doing the calculation. This is about a 8.9% kind of change. Okay, so this is roughly the type of questions. Now, very quickly, I'll take you through another question to explain how beats and Doppler's effect come together, so that we complete all this. Okay, so this next example, something like this: a source of sound and an observer are inside the car, which is traveling at a speed of something. Let us say it's traveling at a speed of 15 meters per second towards a wall. And the frequency of the source is, let us say, 100 hertz. And the speed of sound is 300 meters per second. So we have to find the beat frequency heard by the observer who's inside the car, or who's traveling along with the source. So what is happening is that the observer inside the car, he hears F, which is the direct sound from the source, and he hears, let's say, F prime, which is the frequency of the echo or the reflection from the wall. Okay. So beat frequency that he hears will become the difference of F minus F prime, whatever that difference. Okay. Now this we know, but this we need to calculate. So how we'll calculate this? So this will come in two steps. Firstly, the source is traveling towards the wall at a speed of 15 meters per second directly. The wall is stationary. So the frequency of sound the source was generating was F. So now let us say the reflected sound that is coming from the wall, that is some FR. Okay. So what will be that reflected sound? It will be the sound of frequency received by the wall from a moving source. So it will become V upon V minus V of the source. Times F. So here it will be 300 upon 300 minus 15 times F. So we can use binomial approximation here. So this will become 1 plus 15 by 300 times F. So it will become 1 plus 100 hertz. So it will become approximately 104 hertz. This is the frequency of the sound reflected by the wall. Now this is still not F prime, the sound that the detector inside the car is receiving. So now what is happening? The wall is reflecting back sound at this frequency. So this now becomes like the source of the echo. not of the main sound, but of the echo. And the person inside the car, he's the one who's the detector moving towards it at a speed of 15 meters per second. So the frequency of the echo heard by this guy, that is F prime, that will be V plus V of the detector divided by V times frequency of the source, which is this. So this becomes 300 plus 15 by 300 times 104 hertz. So this frequency becomes 1 plus 1 by 20 times 104, which is equal to 104 plus I made a mistake here. 20, so there should be 5. My mistake. Just make a correction here. This should be 105 hertz. So this will also be 105. So this will become 105 plus 110.25 hertz. This is the frequency of sound F prime heard by him. So now the beat frequency that he hears will be the echo sound that he is hearing minus the original frequency. So that is 10.25 hertz. Now typically 10.25 is too large for beats to be very audible. Beat frequency to be very, for the beats to be very clearly audible and discernible to the listener, it should be less than about 10 hertz. Typically something in the region of not more than 6 or 7 hertz. But in this calculation, this is what we do. If we reduce the speed of the car from 15 to let's say 7.5 or something, this will become much lesser. It will become close to 5 hertz. So it will be close to 5 beats per second. But anyway, so this is how we do application of Doppler's effect along with beats. And this is the type of question which is most important in the application of beats. So there are a lot of problems like this in H.C. Verma as well as the previous year JEE papers. So you can go through all that, and with that you can now complete the waves chapter. So please continue working on waves, do questions from your module as well as H.C. Verma previous year IIT papers and all that. And you can send me directly any doubts and questions you have by WhatsApp. You know my number. Okay. So that's it for today's class, people. Thanks for attending. And I'll send you the recording and the whiteboard session soon.